As Eukarya says, we were established by the Institute for Advanced Studies Act in 1940 on the 19th of June. And so this is indeed 80 years, but it's also 80 years of celebration. It's interesting that the main driving force for the Act and the establishment was one Eamon de Valera. And on Monday evening, we had a webinar to discuss Eamon de Valera's role in the establishment of this great institution. He himself always regarded the foundation of the Institute as one of his greatest achievements. As chair, I became chair in 2010. That wasn't a great time, if you remember, for our country. And unfortunately, it wasn't. The next 10 years were not to prove great for the whole issue of basic research or frontier research funding, and which DIAS is the preeminent within this country in the issue of basic research. 10 years later, I appear to be leaving in the middle of another crisis, this time caused by a pandemic. DIAS, though, continues to exist and grow with a highly ambitious strategic plan, which is being realized. We are heartened that the new proposal program for government speaks about frontier research. This country needs a diversified research base with equal opportunities for basic frontier research as much as orientated or challenge-based research. For 80 years, DIAS has been to the forefront nationally and internationally in driving such basic research outcomes. The country and internationally has benefited from the outcomes of that research, and we will continue to benefit from that for many years to come. We in DIAS look forward to the coming decades and continued success for both DIAS and for our country and for our impact internationally. I very much look forward to tonight's lecture. I've enjoyed greatly the honor of being chair of this great institution, and I wish the people who come after all the very best in the years to come. And thank you very much for this opportunity, Eukarya. And the statutory lectures have been hugely important down through the years. Public lectures have been hugely important to DIAS, and tonight will only add to that. So thank you very much indeed.
Okay. Thank you very much, Vincent, for those remarks. And you've obviously referenced in your remarks the fact that DIAS has had many achievements over its 80 years. Tonight is not about, I suppose, going through or exposing those. And I would just say to the audience to keep an eye out for other events that will be coming up over the next number of months, online events where we will actually be highlighting some of those achievements. We will on Monday be launching a little video which actually, I suppose, summarizes some of the highlights, but not all, but some of them, to give you a flavour of what actually has been achieved at DIAS. And indeed, we will be highlighting very much our current activity. So back to this evening's lecture. Can I thank, on behalf of the Institute, the School of Theoretical Physics for organising this evening's event and taking the lead in setting up this first inaugural DIAS Day lecture. And to say a few words on behalf of the school, I'd like to ask Professor Arthur Jaffe, who is the Landon T. Clay Professor of Mathematics and Theoretical Science at Harvard, who is the current chair of the Board of Theoretical Physics, just to say a few words. Arthur.
Thank you. I'm extremely happy to end my 15 years as chairman of the School of Theoretical Physics Board by welcoming and expressing my appreciation for my friend Gerard at Hooft. He's made striking original contributions to physics, from the proof of renormalization of gauge theories to the foundations of quantum mechanics. As an expositor, Gerard has the ability to illustrate complicated concepts with insights that one can easily understand. I was privileged to co-organize with Gerard a series of summer schools in Corsica to which some of the best young physicists in the world would be to come. And Hooft's research consistently questions conventional ideas. These admirable qualities are shared by the researchers at DIAS and make this institution unique. They've established the well-deserved reputation of DIAS and make the institution special as we look to the future. So let's share the joint excitement in anticipation of the inaugural DIAS Day lecture, which Professor Donjoy O'Connor, Director of the School of Theoretical Physics, will manage. Donjoy. Donjoy is muted.
Thank you very much, Arthur. It's a great pleasure for me to have the opportunity to introduce Gerard Hooft, who has been an inspiration for me from my graduate school days when his first papers were already famous. He is an inspiring theoretical physicist who has made a great effort at outreach, especially to young theoretical physicists. And I always recommend his webpage on how to become a good theoretical physicist to our younger colleagues. You will find a link to that on the announcement for this lecture. I won't delay you further because we're all anxious to hear what he has to say. So I hand over to you, Gerhard. You may share your screen. Thank you.
Is my screen shared now?
Yes.
Okay.
Do you want to put it on full?
I will wait one moment if
Okay.
put it on full. I just want to make a few remarks about DIAS. I first came to know people from this institute in the late 70s, early 1980s, when, in particular, when I was visiting a summer school in St. Andrews, where Laflin O'Rafferty was there, and he was one of the participants, say, of unraveling the standard model in those days. Those were very exciting days in our field, and we were all enjoying one new discovery after the next in those days. If I go further to the past, I see that many very famous names have been have been listed here as professors, among whom Erwin Schrödinger. Schrödinger, of course, had already done his major work in physics in 1926, but he was appointed here in 1941, as I see. That is the time that he was considering or thinking very much about the relation between life on one hand, so biological forces, and the laws of physics. And he was one of the first people to realize that living organisms must somehow contain, encoded in their system, the way in which, in which they function and the properties of species. And he was one of the first to remark that this must have a molecular origin. So people were having great ideas while at this institute. Now, let me know. Can you see my screen? This is the most important thing now.
Yes, we can now.
Okay, very good. So the title of my talk is about black holes and how they might be sources of new physics. I've been thinking about this problem a lot, the latest decades, and again, obtained all sorts of insights and enjoying discoveries and ideas from many people in the area. And I'm very happy to talk about this subject here now. I'm going to relate it to the nano world, the world of the very small things. And that means atoms and the way electrons are rotating around a nucleus in an atom, the properties of waves of light, but also waves in other substances that together are essential in understanding the small particles as we know them. The nano world is, of course, the world of atoms and molecules. And most importantly, the nano world, the way I see it, is a world governed by quantum mechanics. Quantum mechanics is a marvelous discovery of which Erwin Schrödinger was, of course, our main was playing a pivotal role in that with his equation. The logic in quantum theory is really very peculiar, and it seems to bounce right against people's feeling of how the logical world should hang together. It certainly is at odds with my own feeling about how logic should function. And so much so that I've been thinking also a lot about quantum mechanics itself. How can we improve our understanding of what is really going on when you try to describe atoms and molecules and other small things? We know from history that Schrödinger and Einstein both were somewhat or very much worried about what quantum mechanics is really telling us. We understood the equations. The equations are very clear mathematically. And so there's no doubt what these equations are telling us, how to compute things. If you want to do an experiment with atoms, with molecules, with light, even sound, with the way these light and sound and atoms act together in substances, we all know how to do those calculations, and it works fantastically well. It has been an enormous success of 20th century physics. But the strange thing about quantum mechanics is that somehow it seems to represent reality in a way that we don't quite understand. And there's a lot of discussions about this. I think, that this problem of what quantum mechanics is really telling us is such an important problem that we have to use our most intellectual abilities to try to figure out exactly how it works. And I'll explain later why I think it is so important to combine quantum mechanics with other laws of physics to see how everything hangs together. In the history, it always has been the case that when you try to reconcile one domain of science with another domain of science, you learn new things about both of them when you see that they have to go together. So this holds in particular for physics when you try to understand the small things and you try to understand the big things, the stars, the planets, the universe. When you try to combine all this knowledge together, you learn something new. And Schrödinger, as I said here on my slide, was appalled, just like Einstein was, about things being not real. Like a cat can be dead and alive at the same time. So Schrödinger was thinking of the Gedanken experiment, thought experiment, where he uses his cat. And at a certain moment, the cat can be dead or can be alive, but somehow you cannot distinguish any state from another state. There's something very wrong about quantum mechanics says about dead and alive cats. So this is the way we like to represent things. It looks as if when you put a cat in a closed box, you can arrange the events such that at some point you don't know whether the cat will be dead or alive. And the theory seems to be saying it is both. Schrödinger was against that, Einstein was against it, I'm also against that. That I don't believe the cat can be both dead and alive at the same time. But many people have more delicate views about this. And it is so important to understand this because I think eventually the way our science is going to proceed will depend on this kind of understanding. So let me return to the nano world, but go to even smaller things. Now, the smaller the things are that you describe, the faster they seem to move. So the subunits of atoms and molecules are moving around faster than the molecules and atoms themselves. And as soon as they go so fast that they encounter velocities that are participating with velocities that are comparable to the velocity of light, you get something new. Then you have to join quantum mechanics, the laws of quantum mechanics, with the laws of special relativity. That's, of course, Albert Einstein. You've all heard about what he was saying about relativity. The notion of time is becoming a relative notion. It depends who is looking at at time and who is using it. On that, it depends on whether two events are simultaneous or not. So this is so important that it changes again our view of reality. So now you can imagine that when you want to combine a bizarre world of quantum mechanics with an equally bizarre world of special relativity, you get something new. And what this in particular gives is theories for the elementary particles. And this was the exciting time of the 1970s, but it started much earlier, right in the early days of the 20th century, continuing way beyond the 1970s. People were getting better ideas about the subatomic particles, the elementary particles. And you really understand how elementary particles function once you ask questions about special relativity and questions about quantum mechanics at the same time. We want one theory, not two theories, that describe what's going on. It took almost half a century for theoreticians and experimenters to figure out exactly how to produce such theories and how to test theories. We needed more powerful particle accelerators, machines that accelerate atoms and nuclei of atoms and smaller particles to velocities close to the speed of light. And you need to make detectors that detect what actually happens when particles of that velocity collide against one another. And it took a long time for people to really figure out how to formulate this. And the outcome was becoming more and more clear around the 1970s. That's when I started to actively be engaged in all these questions. And together with many other theoreticians, we certainly discovered that what you had to do is make a step backwards first. Don't consider particles, but consider fields. Then consider the rules of quantizing those fields. Quantizing really means that the field equations have to be made consistent with quantum mechanics. And that turned out to be easier than to make the elementary particles themselves consistent with quantum mechanics. So this turned out to be a very useful in-between step. You first quantize the fields, then you discover that fields are carried away by energy packets, and those energy packets behave as particles. This turned out to be a smarter way to describe particles than just to think of particles as points that move around, because then you don't understand how they interact. But now we learned how to describe theories where particles interact. This can be done in many ways. There are turned out to exist many different kinds of quantum fields. So be that as it may, we found that the most important questions are, take all these quantum fields, whatever field you can try to formulate the laws of, and you can then ask, how does fields propagate in space and in time? How do fields interact? And in turn, that turns out to be relevant to the question, how do elementary particles interact? And so it all pointed to, we turned out to converge, and it happened remarkably quickly around 1970, 1980, that all these ideas together formed something that became known as the Standard Model. The Standard Model puts all known particles together. I like to draw it in the way that you see here in this slide, where you have boxes of toys, and when you open the boxes, you find your toys, just like a Lego set. You find that there are all the particles, and particles can have different shapes, different colors, different sizes, different masses, and they can move at different velocities, and they interact. And the interaction turned out to be one of those quantized fields, and it turned out that the rules followed by insisting that you had to obey the laws of relativity and the laws of quantum mechanics, and don't be easy on any one of them, just try to exactly follow those laws. And then it turned out that the possibilities for particles to interact were quite restricted, so much so that you can make lots of interesting predictions about these particles. For instance, in the early days, we only knew about 3 of the quarks. You see here actually 6, they form 3 generations, but altogether 6 kinds of quarks, each quark coming in 3 different colors. Similarly for the leptonic particles, neutrinos, the electrons, and the others, they all fit together and they form a pattern. The pattern looks a little bit like all the patterns that were found by Mendeleev and others around his time, that the atoms that matter is made of also formed a pattern, the Mendeleev table. But now we found that the elementary particles that are the constituents of the atoms also form a pattern, and that pattern is called the standard model. So here we have the particles of matter, the quarks and the leptons, as you see here. Then there are particles that generate forces between these, and those are they are the generators of the strong force, the gluonic particles, the weak electromagnetic force, which came next to be understood, and then another particle which is only discovered much more recently, experimentally, the so-called Higgs particle. I won't say much more about this model. It will be many, many lectures about all sorts of aspects of this absolutely gorgeous model that describes all known particles with ever-increasing accuracy. So this clearly is a success of science. And even though today you hear about all the deficiencies of the model just isn't perfect. We agree also about this, that there are things not predicted by the model. But what I want to emphasize most of all is the things that are successfully described by this model much more accurately than people thought before 1970, when many particles that were known in those days were behaving more like a black box than like something in which you can do any calculations. But now we understood how to do calculations. So yes, this takes care of all the particles known, all the forces known, except for one, and that's the gravitational force. So the gravitational force has to do with everything. It has weight, is heavy, and is attracted to the center of the Earth by gravity, and also heavy objects attract each other by gravity. It is this particular force that is not really described by the standard model in the way that you would like to see it. You can add the gravitational force to the elementary particles in the first approximation without any problem. So you can take into account that when you create particles, that they fall down when you make a particle. We know how to take care of that. We know how to lift a particle. That's not our problem. And we also understand how Einstein's laws about gravity apply to these particles. That is not our problem. But when we want to combine the gravitational force with the other forces, then we find a new problem. In principle, gravity is a very fundamental force. Everything attracts everything else by means of the gravitational force. In particular, large and heavy things. So think of the sun that you see here in this picture, the Earth and the Moon. They all attract each other pairwise. So the sun attracts the Earth, which makes the Earth rotate around the sun. But actually, the sun also rotates around the Earth. But the sun, being much heavier than the Earth, makes only very small movements, whereas the Earth does most of the movements when it goes around the sun. In turn, also the Moon is attracted, but mainly because the Moon is relatively close to the Earth, the Moon orbits the Earth rather than the Sun, although together they all move around the Sun. So there's also a gravitational force attracting the Moon to the Earth. And of course, there's another force that attracts, where the Sun attracts the Moon and the Moon attracts the Sun in the same way. It was understood from the days of Isaac Newton onwards, but it became understood much more in detail when Albert Einstein found out how to describe this law and how to reconcile this with his earlier theories of relativity. This theory was going to be called general relativity. And the remarkable thing is that general relativity applies to everything. So it not only applies to planets and stars, but also to people being attracted by the Earth just as well. And it was Newton's great discovery that this is a universal theory of forces that he could describe in great detail. the next step was made by Einstein, who made it compatible with relativity theory. The consequence of that was, as Einstein discovered, that when things move very fast compared to ordinary velocities, so when things start to get velocities that are comparable to the velocity of light, then you have to take into account that space and time are not as featureless as one normally thinks. One would think that space is just, the stage on which particles and stars and planets move, but that's all. They thought that time was just a thing needed to say at what time you're looking at things, and that is it. Einstein discovered that space and time have much more structure. They are curved. And due to this curvature, you can make new discoveries and new predictions about space, time, and matter. This is a theory of general relativity, and general relativity has the peculiar feature of curvature of space and time. In particular, space, when it's curved, it means that you can draw lines, but those lines don't look at straight lines anymore. These are the straightest lines by which you can connect 3 points. The reason why they don't look straight after all is that they're drawn on a curly piece of paper. So paper is no longer flat, paper is curved, and therefore all the lines on the paper are curved as well. A consequence of that is if you take a triangle, the sum of the angles of the triangle now do no longer add up to exactly 480 degrees, but a little bit more or a little bit less due to curvature. That's what curvature really means in practice. Now, Einstein had also learned about space and time, and that space and time form one manifold that you have to use to describe all the events in this world. And if there's curvature in space, there must also be curvature in time. What does curvature in time mean? Well, it's very simple to summarize what curvature in time means. It means if you now include clocks in your picture, so you not only have the coordinates of an object moving around, but you also have clocks that you can consult. But then you discover that clocks are no longer making sense when you try to combine their feature. You find that clocks can go at different speeds. These 3 clocks that you see here should be just be totally identical. So all clocks are exactly the same brand, and they all go exactly with the same speed when you put them close together. But when you compare, you put the clocks in the gravitational field of a heavy object, such as the planet Earth, you'll find that clocks far away from Earth will tick a little bit faster than clocks closer by, whereas the clocks closest to Earth will tick slower. If you look carefully at the way these clocks tick, this one ticks faster than that. In practice, this is hardly noticeable. This picture here is very strongly exaggerated. In practice, these differences are so minute that you need very high quality watches to notice any difference at all. But today, physicists can construct clocks which are very, very accurate. And in fact, our GPS system is based on clocks that are sent to outer space in a satellite. So if you don't take into account that these clocks move at different speeds, you will not be able to determine your position on planet Earth using those satellites. But general relativity is a very well understood theory. It's exactly known how to make those corrections, to understand the signals from those satellites and to understand what they say about our position on this planet. Now, gravity acts on heavy things. The heavier things are, the stronger the gravitational force becomes, and the stronger the gravitational force becomes, the higher the velocities are that things take under the influence of the gravitational force. A satellite orbiting planet Earth goes a few tens of kilometers or about 10 kilometers per second. That's fast, but not hardly as fast as the velocity of light, which is 300,000 kilometers per second. That's much, much faster. Now, if you take a heavy object such as the sun, and you let something orbit the sun, it already goes much faster than that. So So this means that the gravitational force of the sun is quite a bit stronger. But if you take a star which is again heavier than the sun, but which can generate velocities that come close to the velocity of light, you can imagine that something drastically different will happen. Then you have to take into account the laws of relativity. But let's just consider one thing at a time. What happens to the sun when the gravitational field is attracting its units together, its components together? So the sun consists of matter. Matter is attracted to the center of the sun, and because of that, you at first think that the sun will become smaller, but actually it's only the core of the sun which will contract. And the only reason why it doesn't contract ad infinitum is that there are very strong forces in the center of the sun that ensure that the core of the sun gives a counter pressure. This core wants to expand because it's so hot, and the sun wants to contract because it gravitates. That it becomes an equilibrium. As long as the sun stays hot, that equilibrium is maintained. But the sun is like a furnace. It boils, it burns nuclear fuel, atoms and molecules of different nuclear type are burned by nuclear reactions in the sun. At some point, the fuel will run out. Then the core will no longer heat itself, it will cool down, but then it will shrink. And because it's shrinking now, it will actually not cool down at all, it will heat up again. So the sun will shrink, but again, the sun will not shrink because the whole core is getting so hot that actually the sun starts to expand. So it becomes bigger rather than smaller. And only the core of the sun becomes smaller. But then a new equilibrium is reached. The equilibrium is that new kinds of nuclear reactions will take place in the sun. So the first stage is that hydrogen is turned to helium, but then later helium will be burnt into carbon and even heavier atoms in the interior of the sun. So then the sun will again get hot, and actually it will become much hotter than it was before, because those are more violent nuclear reactions than it had before. So the sun will expand. Actually, the sun will become a red giant star. It becomes so big that actually it might engulf the Earth, which happens in a few billion years from now. The sun will expand so much that the Earth will be gobbled up by the sun. But then eventually also that nuclear fuel should run out. Then what happens? Well, then there's no longer anything that can burn. After the sun has turned many of its atoms into iron, that's the end of everything. Iron is the atom that can no longer undergo any nuclear reactions to become, to generate more heat. So then the whole reaction ends and the sun will shrink and eventually it will stop burning. Now the sun is not big enough to stop this shrinkage, to continue the shrinking ad infinitum. The sun will turn to a brown dwarf, and that brown dwarf is very compact compared to the sun itself, and eventually will die out after hundreds of billions of years. But if you start at a star which is only a few times heavier than the sun, then this process will continue forever. And then the sun will die, but when it's heavier than that, then it's about twice the mass of the sun, a little bit heavier than that, then a completely new phenomenon will happen. The shrinking at the origin, at the center of the sun, will not stop. The sun will turn into something that's not a brown dwarf, it's not a star at all, it is something completely different. It will be called a black hole. Now, you can ask, it would be a very good question to ask, what have black holes to do with subatomic particles? A black hole is very, very big. We do not know of any process in the physical world that would produce very tiny black holes, although we could imagine a process which unfortunately hardly ever takes place anywhere in our universe, because you need to concentrate small amount of matter extremely strongly to make small black holes. In practice, it's very hard, but it's not impossible. The laws of physics allow one to make black holes very small. Then the laws of elementary particles are going to become more important. And you might be interested in asking questions how to combine the physics of particles with the physics of the fundamental black holes. Let me, before saying that, say some peculiar things about black holes. What is so special about them? Well, a black hole will do weird things with space and time. What I've drawn here is two disks. They're not really disks, they are two three-dimensional worlds and time on top of that, which are curved because of something attracting things at the origin. Imagine something like planet Earth sitting there causing an attraction, causing space and time to be curved. What happens when space and time are getting curved even more because the center of this structure is attracting all the matter to a smaller and smaller object. What you see here is actually two regions of a universe which are going to be attracted to each other. And when you think of very strong curvature, then the curvature becomes so strong that you reach a minimum size, and then things don't get smaller than this thing at the center, but actually it starts to connect the black hole. It's connecting our universe with another universe. I'm saying this in a very vague way. And the reason for that is it is very vague. The science here is not very well understood, in particular not by the physicists who only look at general relativity and don't look at subatomic particles. If you do general relativity, you find that it looks as if two universes are melting together to form one. That would be, in a few sentences, what a black hole seems, well, what seems to make a black hole in the first place. This thing here is called a black hole. And this is the structure that you get when space and time contract very, very strongly. As if two universes suddenly get glued together. That is what they want you to believe. That is also what the equations say. So the Einstein's equations of general relativity say this, that this is a new structure that you seem to be getting. But the structure is actually much stranger than you might think. At the horizon, at the smallest region there, time actually stands still. And that is very strange. It's even stranger if you go to the other side. Time will run backwards. Now, when you ask this, you can also ask, what happens if someone falls into a black hole? I have to speed up a little bit because there are important things I want to say at the end if I have still time. But imagine an astronaut going and falling into a black hole. You might think that the astronaut will go and travel towards this other universe. And in fact, according to some science fiction fanatics, that's what happens. The astronaut will go to another universe. But actually, before going to the other universe, what we will see is that the astronaut will actually shrink here and stop, and he will not go through the horizon. We see him standing still here. So it's not true that he goes to the other world, not from our point of view. When we see him stop right at the horizon, never to get into the black hole to see the other side. Well, there's one reassurance. If you would be the astronaut yourself, you would think that you would go straight through. The astronaut himself doesn't think that he's been stopped by the horizon. He goes straight through to where? Well, that's the big question now. Actually, according to the equations, he will go to a singularity. So the astronaut himself and the astronaut seen by distant observers will experience the notion of time totally different. The astronaut himself seems to be hitting a singularity. So his life will come to an end, even for the astronaut. He won't ever see the other side of the world, not according to the most basic equations that he should like to apply. So at the horizon, time stands still, whereas we think time continues. Now, you would think that quantum mechanics is a strange theory. You can think that special and generativity are very strange theories. You're totally right in thinking that. So just imagine what would happen if you combine the two. You combine a strange nonsensical theory with another strange nonsensical theory. What do you get? Well, you are pretty well guaranteed to get something strange and even that. So so particles do strange things there. What do space and time themselves do? And in principle, black holes could be much smaller than even the tiniest elementary particles. So the equations we have for black holes do not tell you how big a black hole has to be. No, the equations allow black holes to be very small, even much, much smaller than the things that we toy with in our machines. And at some point, it must be so that the quantum effects, quantum mechanics must become important. And well, what particles and antiparticles do is that they fluctuate, they form vacuum fluctuations. And you can ask now, how do these vacuum fluctuations behave when you are very near the horizon of a black hole? The guy who gave a marvelous answer to this question was a genius, Stephen Hawking. And I have a lot to say about this picture, actually. Stephen Hawking here is posing with Einstein and Isaac Newton on a picture when he was playing a role in Star Trek. But Hawking made a marvelous discovery. Hawking asked himself an important question. He asked, how do elementary particles behave when a black hole is eating them up? And then he couldn't get any sensible answer. So he said, oh, let's first ask the question, suppose I have a black hole without particles, but there are vacuum fluctuations that temporarily produce particles. What happens to that? Again, he got a nonsensical answer until he realized that the answer was, you can't have a black hole without particles around it. That would be at odds with the laws of physics. There must be particles around the black hole. And if they aren't there, the black hole will create them. And when the black hole creates the particles will come out. So particles do come out of a black hole, even though all the physicists before him had restrained the black hole to be such that it can only absorb things and never emit things. Now, Stephen Hawking discovered the black hole can also emit objects. So that means Hawking really realized that immediately, that if a black hole emits particles, it will lose energy. If it loses energy, it will lose mass. If it loses mass, it becomes smaller. So even if you don't have a small black hole, take a heavy one and just wait. Well, if you take a black hole as heavy as the sun, you have to wait many, many times the age of the universe before it can become so small that it starts to evaporate. But in principle, the black hole will evaporate. More to the point even is that when it evaporates, the intensity of the radiation actually increase. Even though the black hole becomes smaller, the intensity of the radiation will become much, much stronger. So the black hole will lose energy faster and faster and faster. Where does this go? Well, the only thing is the black hole will explode. So Hawking then asked astronomers, do you see strange explosions in the universe around us? Astronomers said, yes, we see them all the time. They're called gamma flashes. So Hawking got all excited, but then the astronomers really assured him that those gamma flashes are not black holes because they're associated to galaxies. And inside of galaxies, there are black holes, very big ones, not small ones. And those big ones cause very much more powerful energetic explosions than the small black holes that evaporate. So they're not the things that Hawking hoped that they would be, but they are equally interesting, of course. And now we want to understand where these Hawking particles come from. And now you hit the real questions of quantum mechanics in combination with black holes. So the horizon of a black hole seems to be a strange place. Time stands still. But that's only strange if we look at the black hole from the outside. But what will a particle see when it goes into the black hole? Well, for a particle going into the black hole, time will not stand still. No, time will just proceed. And the questions asked there are very similar to the question you can ask, what about the North Pole on Earth? What is the latitude of a traveler who travels to the North Pole or the South Pole? And when he goes to sit right on top of the North Pole, what time of the day will it be? And you realize that you cannot define the longitude of an observer on the North Pole, because the concept of longitude does not exist. So similarly to longitude not existing on the North Pole, we have the time doesn't exist on the horizon of a black hole. The time parameter on the black hole is just like longitude is on the surface of the Earth. So think of the North Pole and think now of a polar bear going there. The polar bear stands right on top of the North Pole, and you can ask the polar bear, what time of the day is it? And the polar bear will not understand you, of course, but he will do his polar bear-y things on the North Pole as if nothing was wrong with his coordinates. So the polar bear doesn't care about the non-existence of longitude and that latitude somehow stops. The polar bear just continues life. Similarly, when you put a polar bear on the horizon of a black hole, the polar bear doesn't care about time standing still. No, he does experience notion of time just like anybody else. But the way we see the polar bear is now totally different. And so this is what you have to understand when you describe the space and time near the horizon of a black hole. So for the bear and for the astronaut going through the horizon, time doesn't exist anymore. Now, an antiparticle is a particle going backwards in time. That's in a few lines, a little bit too easily said, what an antiparticle really is. It's the opposite of a particle. You could argue an antiparticle is a particle going backwards in time. But for the astronaut going through the horizon, the distinction between antiparticles and particles disappears because time doesn't make any sense anymore. So also going backwards in time doesn't mean anything. The astronaut will turn into an anti-astronaut when he goes through the horizon. But exactly how it happens, the astronaut himself is totally unaware of this. So Hawking discovered how to translate the laws of physics at this horizon of a black hole into laws of physics as experienced for an observer outside. And if this way he found out that the black hole actually emits particles. So now you can ask nasty questions. Are black holes themselves fundamental particles? Do you have such a notion as an anti-black hole? How do the laws of quantum mechanics work near the horizon of a black hole? How does it happen that black holes make particles? And what you find, it doesn't make sense. The equations in our textbook are not really made for answering such questions. They don't make any sense. Just like the equations in Einstein's early days, the question, what happens when you go faster than the speed of light? What do you see? That equation didn't make any sense. Or that question didn't make any sense because the equations were not understood. So when Einstein started to understand the equations, he could finally answer such questions. Now we have the same situation here. What about this other universe, these two universes connecting in a black hole? What does that all mean? How does information go from one universe to the other universe? Can we send an explorer to this other universe and ask him what the other universe looks like? And can the explorer come back? The claim is this is not going to be easy because time will stand still for us when the explorer goes through the horizon. So something is very wrong about such questions. So what we have to learn is how to ask the right question. Now, the only way to answer such questions for Stephen Hawking was to say that the black hole itself does not obey the laws of quantum mechanics. Now you can say that, but isn't that very strange? We used the laws of quantum mechanics to define the behavior of a black hole. But now Hawking says the black hole itself is not a quantum object. How can that possibly be? Well, you could think a black hole should be a quantum object. Look, here's a picture that has particles collapsing here into making a black hole. The black hole will continue its life, it will evaporate, and finally it will end up emitting particles again. And all this is like a particle process. Why should a black hole not behave as a fundamental particle? And very early on, as a particle physicist, I've always claimed, no, a black hole should behave just like elementary particles, but we will have to figure out what the laws are. A book was written about this by my friend Lenny Susskind, and we agree that the black hole itself is, well, according to Hawking, the black hole itself should be worse than Schrödinger's cat. We believe that cannot be right. Not even Schrödinger's cat can be dead or alive at the same time, but a black hole cannot be worse than that. It should be an ordinary particle. Susskind wrote a book called The Black Hole War. He described the situation as a war between different physicists of different backgrounds. The particle physicist leading one army and Stephen Hawking leading another army, and the two armies were fighting each other. I agreed with Hawking about his issues of black holes, but I did not agree that this was a war. No, we're all friends together and we argue and we have a difference of opinions, but we are not at war with each other. But we are fighting, but we're just fighting for the truth and not for being in power of something. Anyway, this war became more and more interesting. For a moment now, I'm going to address for a few moments my colleagues. So I'm going to say things which are a little bit more different for someone who is just in the general public, wanted to know something about black holes.
Gerhard,
show a few diagrams.
Do you want to take a few questions before you move to that?
I can do that. That is perfectly fine. I don't know how much time I'll still have. I was planning to spend a few more minutes on these diagrams, but this is a perfect moment to interrupt and have some questions. Yes.
I can give you 3 or 4 and we can just move on from then. We can leave the others. There are many questions. The first one I have here is from Emilio Garcia, who asks, would it be possible to create a black hole in the laboratory?
That question has been asked by many people, actually. Certainly not by any means that we know of. And the reason is that you need such enormously high pressures that there seems to be no material on Earth that can withstand such pressures. So, and that's not by a small margin, no, it's by many, many orders of magnitude. So you can take diamond, you can think of even stronger materials, you can take subnuclear material, but all that is not strong enough to make a black hole. In fact, it is believed that the tiniest black hole of all is extremely much smaller than an elementary particle, but also extremely much heavier than an elementary particle. By the same factors, about 10 to the 20 times smaller than the smallest particles we can think of. Also 10 to the 20 times heavier than the smallest, the heaviest particles you can think of. So you can't combine all this in any practical experiment which would be necessary to make a black hole. But you can dream of colliding particles with ever more force and ask, maybe we can collide particles so fast that they can make a black hole. But you have to modify the known laws of physics by such an enormous amount that in practice it doesn't seem to be possible at all. Not even by us, but also by nature. You can think of very strong accelerators in way out in outer space, in the interior of very heavy stars. But even there, we don't believe that black holes will naturally form unless you really change the laws of physics as you know them today by a very, very big margin.
There are 2 other questions, one from Tricia and another from Aaron Dinesh. How can light and matter go through the event horizon and never come back if quantum theory states information cannot be destroyed? And the second one is, if black holes emit particles, does that mean that these particles travel faster than the speed of light?
That question has been a very central question in our disputes about black holes. And unfortunately, just because we cannot see a black hole from close by, there are many light years away as far as we know. And so we cannot do experiments with black holes very easily. And even if we could do experiments, those black holes would be very, very large and heavy. And even there, particles would not be undergoing the quantum effects that we would like to investigate. So we cannot do such experiments. But we can imagine what happens. So we can do experiments in our minds, just as Einstein made experiments with his mind rather than using any experimental apparatus. So in our minds, we can imagine what happens. And now, as you can imagine, not everybody agrees because we don't know what's going to happen. So there are different theories. My own preference is a theory where indeed a black hole gobbles up matter, but those matter particles are then at the horizon at the same spot where the outgoing particles are being formed that get out of the black hole, and they come out in a chaotic way. They don't seem to carry information, but as a matter of fact, they carry lots and lots and lots of information. So these particles form such complex patterns that in principle, they form as much, if not more information than the particles that went in. But we are in no position to encode, to decode this, this information. So we cannot read what comes out, but we can theorize about it. So my preferred answer is that the information does not go away, but is transmitted onto the outgoing particles. Now, then people ask me, what is that mechanism that causes this way of information transmittal? And they claim that you can't have it, but I disagree with that because it's the gravitational force itself between in and outgoing particles that is perfectly well able to transmit the information from in to out. And you can even quantify this mechanism in such a way that you find, yes, information comes out, but no, we are not yet in a good enough position to compute the details because many details of the theory are not so clear. But at least the potential theory can be made, but by trying to answer the question better, find the equations, find exactly how all the equations close, I am convinced we'll enter into new physics and find new answers to all sorts of questions, including eventually the question is, what made the standard model the way it is? We don't know how to answer that question. I think all these questions will eventually be related. But this will probably last many generations of scientists or physicists to figure out how to answer this question properly.
The next question is of political nature, so I will leave it until the very end because it will distract from us. How can, this is from Carol, how can an outside observer see a black hole gain or lose mass if an object on the horizon appears to be static? Thank you. We'll leave it, and we'll, after this question, let's return to your talk. Okay.
Okay, the point is that the black hole is static, but only if you add all particles going in and all particles going out. So if I take a very large sphere, I draw a very large sphere, much bigger than the black hole, just around the region that the black hole is occupying, but also surrounding space and time. In the inside of the sphere, there are particles going in and particles coming out. In the total mass of that big sphere is conserved by the laws of nature. But then if particles go out, then, and as soon as you say those particles leave my sphere, then what stays in the sphere, by definition, has a smaller mass and smaller energy. So a black hole can lose mass by evaporation just exactly the same way as it can gain mass by absorbing things. All black holes in the universe absorb much, much more matter than it can also possibly emit, because the intensity to Hawking radiation of observable black holes is so tremendously weak that in practice it absorbs much more than it emits. So black holes grow and don't shrink. But even if it would shrink, that would not be at odds with the laws of nature at all. So of course, these questions are all related. This is related to the previous question. And only by answering all the questions at the same time, which is very much a circular problem. You can only answer one question after answering the other one, but it's circular. So we don't know how to do this properly, and that's our difficulty. That's what we are scientists for, to figure out how to get out of this circular problem.
Okay, thank you. Let's continue with the transparencies.
If I have still enough time.
Yes, we won't restrict your time like that.
Okay, thank you. So this is a so-called Penrose diagram. it represents space and time before the black hole went in, and space and time surrounding the black hole, and also space-time after the black hole is sort of evaporated. This is the Penrose diagram that many people think of. A Penrose diagram is a diagram where you draw space and time in such coordinates that the speed of light is always the same value. So the speed of light is 45 degrees here. Again, this is, for some people have heard a little bit about black holes before. This is the Penrose diagram people like to draw for a black hole that was formed in the past. It was formed out here. Then an observer sees a black hole, that observer sits here. And then an ingoing observer eventually will hit the singularity, that singularity sits here. This is good if you want to include the formation process. But if you want to know what a black hole does millions of years after that, you can still say this part is still there, but it's not right to keep it there. And this is what I've been trying to explain to my colleagues. We have to chop this bit off and replace it by another diagram. And that, oh, I forgot to magnify this. Sorry, a moment. This diagram that I wanted to show. And this is the next diagram. This looks totally different. This is also a Penrose diagram, but it describes a black hole in this domain. It describes a black hole that never has been formed. That is to say, it has been formed in the infinite past. A black hole that never decays. It decays in the infinite future. Real black holes will have been formed millions or billions of years ago, and they will decay millions or billions of years after this. But what we are really interested in answering the questions, such as the last two questions asked to me just before this, to try to answer those questions, you need a black hole only through a time period of a couple of seconds, not more than that. So you don't want to include the history of its being formed, and you don't want to include its final stages after it evaporated completely. Then you get a black hole that looks like this, and only then you have a black hole that has a corridor going to another universe. This region, this square here, tilted square here, is a diamond, is labeled 1, that's our universe. This is another diamond that looks exactly like the other one, labeled 2, that's another universe. And they're connected here. The polar bear will not know in which universe he's sitting in when he sits here in the middle. This is a diagram you have to use. However, in this diagram, all particles that you put here are weakly interacting particles, which only have a small amount of gravity. So when you want to understand the quantum behavior of the black hole, you have to say, I only include particles which don't gravitate too much. Whereas if you wait a very long time, then that means you're including the particles that evaporate, which eventually represent a lot of mass, and the particles which made the black hole represent a lot of mass in the past. If you include those, then you have this previous diagram that I have here. But now, if you don't include those, you have this diagram. And this is the diagram you have to use. And then you get into totally new things. Then you have to say particles going in and out not only live in this universe, they also live in that universe. However, time runs in the opposite direction. So you put particles on this slice here. This is a slice at a given time. And the slice moves to the future from past to future here, but past and future here is interchanged. So here this diagram, this slice goes backwards. This is what we call the Cauchy surface. And this is what the Cauchy surface you have to use. And just if you show these pictures, this is how the Cauchy surface proceeds in space and time. If you do this, you get a totally new insight. However, you're still puzzled by one thing. What is this other universe? And people usually think that this other universe represents somewhere else. If you tunnel from here to here, you end up in another universe. Remember, however, you end up backwards. You are going backwards in time here. What kind of universe is that? Well, the better option is, this is the same universe as this one, but seen from the other side. What do you mean seen from the other side? Well, seen from the other side of the black hole. And that turns out to be the only answer that makes sense. You are seeing the black hole from the other side. And that means that the black hole picture that one should have is that the black hole is what I call a vacuole. This blue region here is space and time. Space and time is highly curved. But then there is a region cut off. This inside is not space and time, not even vacuum. It isn't really there. If you would move from here to here through this white region, you immediately step from this cross to that cross. You never travel from here to here at all. This cross is glued together to that one. This circle here is glued on that circle. This circle here is glued to that one. And there is no inside. So you have to think of this space and time being glued together. That can only be if space and time are highly curved. That's what they are near a black hole. So that is a view of space-time that comes out of this picture. And I think it's extremely intriguing. It could be that the entire universe is filled with such kinds of space and time. There are many more of such vacuoles. If you add quantum fluctuations, you get many, many more of these. You get a completely different space and time than we think of. Maybe this is a space-time that we have to use in order to understand how to do quantum physics. But this is going to affect the standard model. So this could bring a completely new picture of how we have to handle particles themselves. I don't know whether this is true. We don't have the right equations. So we don't know how to proceed here. We have to, or this, I didn't want to show these pictures. Okay, there's one picture missing, I see. I had a picture which is apparently not in, oh well, never mind. Then this is the end of the picture. This is how space and time can be non-trivial. If you move faster than light, you re-emit at the other side. Let me see, we have, oh no. Oh, this is the picture I wanted to show, that somehow my pictures were in the wrong order. This is normally, again, this wormhole connecting two universes. But now what you have to do is, this is not this thing underneath is not a new wormhole. This is just when you would leave this spot here, you'd be like a polar bear again, but the polar bear is glued from here to here. So the polar bear will come out again, but come out at the other side of the black hole. Also back to front, you come out as an anti-polar bear, whatever that means. So a particle is turned to an antiparticle coming out to the other side. And if you tell me that doesn't make any sense, I would agree with you. So this only makes sense when you do quantum mechanics near the black hole. Clearly, we're going to see saying something very important about space and time, but we don't really understand what this means. So you can ask lots of questions about this, to which I have no answer, because we're still trying to figure out how to put all this in equations that all together hang together so tightly that we get new physics out, new theories. Hopefully, in the very end, it'll tell us why the standard model of subatomic particles has the shape it has. We have many questions there that we don't understand and we won't understand very, very badly. I know this institute, DIAS, is also involved with cosmology. In cosmology, these things, similar things can happen that are very strange. We want to understand how the very beginning of the universe got into being and how the universe got started. And there again, you have to ask questions of very similar nature. So all these are very important questions, and they are totally unfamiliar domain today. Many mysteries still hanging around. As I said, many more generations of scientists will be needed to answer these questions. That's why I hope that this institute will have a future as great as its past, of scientists figuring out how to deal with this situation properly. I only give you a glimpse of what kind of things you might expect if you try to dive into this very interesting material. But I'll end my talk here. If there are more questions, I'm quite happy to answer. Thank you very much.
Well, on behalf of the audience, let me thank you, Gerhard, for a wonderful exposition. I can tell you that the number of questions indicates that the audience is very enthusiastic about your lecture. The format doesn't easily allow for applause, but I will, on behalf of them, thank you. Right. So I can move to questions, some further questions. There are a very large number of them, as I said. So we'll try and get through as many as you have, as you can. From Raymond Ishachi. I'm going to mispronounce most of these names, I'm afraid, so forgive me. We have participants from the US and from Japan, as far as I can see. So we're covering the globe.
A moment, Denjo, is there a chat page where people write
there is a chat page, yes. You should be able to see it.
I don't have it on my screen. I don't see how to get it.
I'm not sure how your screen works, but it should be on the, if you move your cursor around, the chat screen usually pops up, but I can read them to you.
Yes.
So from Raymond.
No, I don't.
From Raymond, the question is, what are your opinions on possible resolutions of the black hole information paradox, such as firewalls and fuzzballs, etc.? And do you think that a cherished idea in relativity or quantum mechanics, such as preservation of information in quantum mechanics, will be subject to change in a future quantum gravity?
Yes, I do have very strong ideas about those. The firewalls that people talk about are really streams of particles which are on the horizon of black hole. This cross here at the center represents two horizons. There's a horizon that you encounter when you go into the future and you dive into the system along these lines. So here you are in our universe, you dive into the horizon this way. But there's also a past event horizon, which is here. That's if particles come out of the black hole, they come out from this horizon. And these are particles coming out, and these are particles going in. And here it goes in the other direction in region number 2. So these firewalls you get if you try to understand how the information of outgoing particles is carried out, if you want to somehow ignore this part. But the very important thing is this part is there, and you have to ensure that the horizons are lines, they don't stop here, but they continue to the other side. So
the next question is, would horizon 2 on the opposite side of black holes consist mostly of antiparticles, since the matter we are made of must have its counterpart somewhere? And would this be related to dark matter?
Indeed. Now, there's something very interesting if you study quantum mechanics itself. In quantum mechanics, we have this problem of reality. And I've been trying very hard this last couple of years to see how I can give a more real interpretation of quantum mechanics. If you do that, you find that the concept of energy doesn't range from 0 to infinity, but from 0 to a maximum energy. Very often that happens in quantum mechanics. If you have a maximum energy, it means that no longer, not only can you have a vacuum, so here we have something very close to the vacuum of a black hole because there are very few particles around. But when it goes through the horizon to the other side, you connect this not to a vacuum, but to the space, the time opposite of vacuum. And that is the completely full space. So there's a completely empty space here, a completely full space here, where the energy is maximal. You see, vacuum is by definition a space-time out of which you can annihilate nothing. It's the lowest energy state. So region 1 is the lowest energy state. This region 2 is in the highest energy state. And so if you don't understand quantum mechanics, you can't really say what highest energy means. And people will rightly object that highest energy means that all these particles will gravitate like mad. It's an enormous amount of energy. All this energy will represent an enormous amount of gravity. How can you have a highest energy state here? The answer is yes, but I first decided to throw away all the gravitating particles. What I'm left over with is particles that do not have gravitational forces. Now I can imagine the highest energy state here. But those very energetic particles are the particles which went in long ago. They're all here. If you put them black in, then you don't see this region 2. You see this previous Penrose diagram I had before, this one, which where you don't see region, well, you see some region 2 here, this is then region 2. In my diagram, that's really region 3. Region 2 is then forbidden. So, so you don't see those particles anymore. But when you go over to this diagram, not only those very high energetic particles have disappeared, also the firewalls have disappeared. If you allow particles to go in here and here at the same time, and you allow them to go out here and here at the same time, then you will describe one hemisphere of the black hole together with the other hemisphere of the black hole, then you don't have a firewall either. So the firewall disappears, and I can explain in equations what happens to the firewalls, but I haven't got the equations in my slides here. But what happens with the gravitational force is they move particles around on this horizon. So they move particles from region 1 to region 2. That's what gravity does. So now you see that region 1 can no longer be separated from region 2, like it could be done plastically. And then you get this firewall. But the firewall disappears if you rearrange particles and antiparticles in the way which I suggest. However, I should add to that, I don't have all the equations. So because of this, I can shout like mad to my friends, look, this is how you have to look at things, but you don't have all the equations. So as long as I don't have them, they won't believe me. And so they have their firewalls.
Yes. Would quantum mechanics prevent gravitational singularity? And what happens when two black holes collide? And would it be possible to make a black hole out of light? Those are the next three questions.
Okay, first thing, if you look carefully here, you see in this pendulum diagram, the singularity lies here, which is you go through the horizon, you go through it, and then you don't enter to region 2, you enter into region 3, it's called here. And into region 3, you'll be killed by this singularity. You can't go faster than 45 degrees, so you'll travel in this direction, you'll be dead. But this singularity is neither seen by this observer, nor is it seen by this observer. These can only see their own diamonds, their own fractions of the universe. They can never see this. So the singularity does not play a role in any observations. It is comparable to the singularities you get if you take, say, Kepler's laws of planets moving in ellipses. What you can do with a planet moving in an ellipse, you can ask what happens when you go to complex time. Then the orbit of the planet goes to singularity. The planet itself never is destroyed by that, because we never go into complex time. It's impossible. Time is a real variable, that's it. So don't worry about the singularities that the planetary orbits have in complex time. But they are there, those singularities, but they don't play a role. Similarly, this singularity doesn't play a role. I believe it never plays a role if you have to complete the equations, which I don't, and therefore I cannot, again, answer the question with all confidence and all certainty. But it seems that the singularity is not there.
Okay, thank you. I have one from Samuel Kovacic. On a slightly unrelated note, the dark matter experiment Xenon reported excess of signal close to 1 kV. Do you think this might be dark matter or just underestimated of the signal? That may be slightly off topic.
I've heard about this finding. Also, I've heard that they're not yet completely sure whether it could be a fluctuation in the findings or whether it could be an error observation. So one always has to ask these questions. The problem with experiments is that the first time you notice something, you can never be sure. It could be a fluke of experiments. So my best guess is that this is something that will go away, but it could also be something physical. And I can only repeat what I read in the newspaper, that they think it could be neutrinos with very high magnetic moment. That doesn't seem likely to me, because the standard model works so well with neutrinos having the magnetic moments that you compute when you calculate how neutrinos behave. It's very difficult to imagine, but not totally impossible. So maybe there's something of this sort going on. Some extension of the standard model. It's always possible. We're all hoping that one day the standard model will show extensions which show new features of physics, but I think it's a little bit too early to tell.
If a black hole, this is from Manish Manuel, if a black hole has a universe 1 and universe 2 on both the end, and an astronaut or particle travels through one and enter into another. It won't come out from the black hole, which is in universe 2. If the black hole is I'm not quite getting the question. How would the particle that can be pushed out from one side of the black hole, how can it be? I'm not quite sure what the question is stating. It's others.
Well, if you look carefully at this Penrose diagram, you see universe 1 here and universe 2 here. This cone here shows how the speed of light goes in this diagram. And the rule is that when you have a heavy object moving, it always stays inside its line cone. It means that it travels at a orbit which is tilted by less than 45 degrees with the vertical. So in other words, if you go from 1 to 2, unfortunately, you can't go to 2 directly because you would have to go faster than the local speed of light. So the only thing you can do is go from 1 to 3. And then you will never get out anymore. You'll be eaten by the singularity. What gets out is something else. What gets out is the information that the particle moves from 1 to 3. And that information is carried in its gravitational field. Because remember, everything gravitates. So everything carries information. And that information travels in the other direction. So the guy goes in, but the gravitational field it generates is a little bit like the Fourier transform of the object going in. And the Fourier transform has opposite space-time properties. So when something travels in this direction, the information coming out travels out in the other direction. And that information, that makes it to the other universe, region number 2. But that information is completely garbled. So the astronaut himself will not come out, but the information that he represents will. And that is carried along by his gravitational field. Now, the gravitational field for an astronaut is far too weak for us to even measure it. But in this strange physical world, that gravitational field carries all his information in a completely mixed up way.
From Tricia, would the force creating black holes oppose vacuum decay? And from Roy Lonergan, is the behavior of the surface of the black hole related to the geometrical nature of GR?
Well, when you look at this picture here, you'll find that this is a kind of picture we have in our minds as we should like to describe black holes this way. We have not succeeded completely, but anyway, to some extent we have that there are particles going in, making a black hole. There are particles coming out, which represent the, I touched something, I think. Or this is again. So we are so we're making black holes and it decays again. Now, if you look more carefully at theory of elementary particles, you find that all the particles that you have, if this is a Feynman diagram, and it looks a little like a Feynman diagram, if this is a Feynman diagram, then the number of particles that goes from here to here and there is finite. So the number of black hole states should not be infinite, it should be finite. And indeed, that's also what Hawking gets. When he computes the thermal properties, he finds that the particles coming out of the black hole have a certain temperature. If they have a certain temperature, you can compute the entropy of a black hole. If you can compute the entropy, you can compute how many quantum states the black hole can be in. That is strictly finite. But every quantum state will be allowed to decay into another quantum state and the emitted particles. So particles are emitted and in all sorts of ways. And every time the black hole emits a particle, it changes it into something else. The picture should be completely logical if you can say that a black hole can be only in a strictly finite number of states. But you see, all these states are unstable. So because they're unstable, this is like a heavy atom decaying to lighter atoms, or having, say, uranium going through a long nuclear cycle, ending up as lead eventually. So you can compare these decays this way, and the number of nuclei that you find in the radioactive decay of uranium is just a finite number of states. Similarly, we expect the black hole to form a finite number of states, much more states than an atomic nucleus, but still a finite number. And it all hangs together qualitatively very well, but we don't have all the quantitative problems in closed equations.
Alexander Guittardi says, thank you, Professor Hooft. And Sinead Mannion says, thank you. I like the polar bear idea. The Ahmed Ashraf, my question is from the first part. When we say that the standard model is not perfect, are we saying that we need to modify it, or we need a new theory to describe that system?
We need both. So here's a standard model. It looks like a beautiful unit. And as a physicist, I think all physicists agree, it forms a beautiful unit. You don't need to add anything at first sight. So at first sight, you'd say, look, this is a renormalizable theory. We can fit the masses with the observations. We can calculate everything we want, nearly. And everything would be finite except that. There are little problems with it, of two kinds. There's a problem with the pure mathematics of the theory. When I say I can compute everything, actually I'm lying. Because if you want to compute anything with any accuracy, that's something else. In fact, the strong interactions caused by these particles here are so strong that calculations very quickly run out of hand. And we don't know how to compute things as accurately as we would like to do so. So there's a limit here. Then there's another limit when you go to extremely high energies. Then these forces here, particularly electromagnetism, will go out of control. Very slowly, but definitely it goes out of control. So the model by itself is very, very good mathematically. We can do extremely accurate calculations, but not infinitely accurate. And also it doesn't really apply to all possible energies. So it's less than perfect. Well, we are only very happy with that because it means that there's something to be improved. But then also you say at the level where particles reach what we call the Planck scale, where they have ridiculous amounts of energy, ridiculous amount of mass, and ridiculously small. At that stage, the standard model just explodes. It doesn't make any sense anymore. It has to be replaced with something better. Now, you can also say right away from looking from there at this looks like a pretty complicated toy. Why are these all different boxes not forming one single box of particles, all related to each other by fundamental mathematical equations? They don't. So we also say this theory is mathematically not as good as it could have been. And there are many theories about this. The problem is these theories are very difficult to check experimentally. As far as they could be checked, the experiments are always against it. The experiments say, this is the best we have, this is what we can confirm, but we cannot confirm anything else beyond it. So we just have to guess our way around. People are good at guessing, but not hardly as good as they should be to figure out how to do this properly. So yes, I think the answer to the question is both. We have to improve the theory, and we have to fit it into the theory which has the gravitational force right in the middle. This should be one box, not saying a standard model, but saying it's gravity.
Donica says thanks. Trish says thanks, and for a fascinating talk on space-time is fascinating. It encourages people to look to Google LIGO. Emer Cunningham, what a fascinating lecture! What a privilege to have been able to learn from such an expert and communicator. And David Moore has a more technical question. I believe that the astronaut falling towards the event horizon sees time speed up in the outside universe. At the event horizon, time would speed up infinitely. Doesn't this mean that the largest black hole would evaporate just before he or she crosses the event horizon, or at the very least, the astronaut sees the end of the universe just before crossing the event horizon? And
well, this is again the question of the polar bear.
yes.
The polar bear doesn't see anything exploding at the North Pole. If you ask a polar bear, he walked to the North Pole, and he says, "What do you mean? I'm on this ice here," and I don't see anything exploding. Same thing, we believe that this astronaut going, let me try to find the picture back. Where is it? Oh, it's somewhere behind here, I think. No. Oh, this is the picture. I should. So this astronaut, no. Where is it? So here you have that for the astronaut, yes, you would think naively that if the astronaut, if the clock slows down for us when you look at the astronaut, the clock should speed up for the astronaut when he looks at us. That's not quite true. However, the astronaut may easily change his course and watch everything coming into the black hole, whatever has been sent to the black hole during its entire lifetime. That would be, of course, very singular. But the astronaut could also decide does he continue his way inwards. And while he goes in, he always stays ahead of all the particles sent in later than him into the black hole. So he will not be killed by matter, by the signals from the outside world, because the signals go through the horizon too late. He's already here, signals are still coming behind him. So whatever you learned about special relativity is already strange. The special relativity doesn't say whose clock goes faster than whose other clock, which clock goes fast, which clock goes slow. That's determined by who you are and where you're looking at, how you define time. It gets even worse in this case. So you can't really say that for this astronaut, the signals from the outer world are infinitely blue shifted. It's not that simple. It depends on where your journey is bringing you, whether you will see all these other particles sent to you or not. So if the astronaut here decides to turn around and wait until he sees all the particles sent after him, yes, you'll see all the particles seen by emitted to him during the entire lifetime to black hole, which of course is quite a lot, and that will be highly blue shifted and might even kill him if he's not careful.
Elena Taskova says, thank you very much for the lecture, Professor Hooft. And Eslam has I have a question regarding particles coming out of the black hole. They pass by the black hole horizon where time stops from our point of view. So how can they reach us? And there's one last question, so I'll read it as well so we can close questions, and then I'll hand back to you, Keria. Wonderful lecture. This is from Cormac O'Rafferty. Wonderful lecture. Many thanks. Do you feel supersymmetry is essentially ruled out by experiment, or are you optimistic SUSY particles will one day be found?
Okay,
So those
two questions.
Two very different questions, but I'm closing questions at this point.
Okay. So, so the first question is the outgoing particles time stands still. Again, think of this polar bear. The polar bear will walk from one longitude to another longitude in a split of a second, because for him time is something else. But here you see the outgoing matter. The ingoing matter goes in this direction. Let me see. Oh, I had. Let me see where no. I'm looking for a slide. Yeah, here. These arrows are the path of ingoing matter. It goes into the future horizon. If you send out a signal just a microsecond before you went into this future event horizon, you might have been sent out a signal. A microsecond later, you send out another signal. But for the outside world, they only come out here. So the outside world has to wait forever for your signals to see them. The signals sent out after you pass the horizon will never reach the outside world. They will reach singularity instead. So you see that's the time dilatation as experienced by an ingoing particle. Now the outgoing particles come out from here. That's the other way around. So the outgoing particles come out at time equals minus infinity. This is really time equals ancient ages ago. Before that, there was not even a beginning. The particles seem to come out of the past singularity that you see here. And for them, it's the other way around. So they come out, the outside observer here will see these particles as normal particles. But here, they'll be described as particles with infinite energy. So infinite energy coming out. Here you see the particles going in with infinite energy. And it is at this spot where these infinite ingoing particles, infinite energy ingoing particles, interact with infinite energy outgoing particles. That interaction diverges gravitationally. So the gravitational force diverges here. And that's why we have to rearrange the equations. And that's how the whole thing starts to hang together if you add in all the equations. But you see that notion of time here is something totally different from notion of time here. The last question is about supersymmetry. I did not mention supersymmetry in my talk. I also did not mention superstrings. And many of my colleagues start right away with chapter 1, talking about supersymmetry, super black holes, and superstrings. I think it's a little bit premature to think that you have to use supersymmetry or superstrings in this description. I've always done without, just because I've always argued if supersymmetry and superstrings are the answer, I'll have to bounce into them. By arguing this way, I'll have to find out that supersymmetry is there, and I have to find out that superstrings are there. I haven't found that out yet. So far, it seems that supersymmetry and superstrings, they're very interesting theory, very suggestive, full of brilliant ideas, but they have not been checked experimentally. Whereas general relativity and quantum mechanics and special relativity are all theories which have a very, very solid tests experimentally. So those you have to believe. Supersymmetry, we don't have to believe. Superstrings, you don't have to believe. They may well play a role. I won't say, you won't hear me saying that these theories are wrong or incomplete or anything, but they're just highly speculative. And I want to know what is not speculative, what do we know for sure, and those are the things that I'm using here to arrive at the theory. And at the very end, you might say, well, I believe in superstrings, fine, but then they often describe different kinds of black holes, which are not as general as the ones you have here. This is the so-called Schwarzschild black hole, the one originally proposed by Schwarzschild right after Einstein gave his equations for general relativity. Karl Schwarzschild, the astronomer, found a solution, and that turned out to be this solution. And the predictions of the general relativity from that day on always have been, as far as possible, been confirmed by experiments. But the string theory and supersymmetry are really in a different phase of science, I believe. That they're highly intriguing models, but still in the phase of religion rather than in the phase of real observable physics. But the most important problem I have with supersymmetry and superstrings is that they always work with different kinds of black holes, and these black holes, as you may or may not believe, are relevant for nature. But this one is definitely relevant for nature because they are there. You see them in the universe.
Okay, thank you again for an outstanding talk, and I will pass to Eukarya, and she can pass to anyone else.
Okay.
Afterwards.
Thank you very, very much, Gert, for the fantastic talk and lecture this evening. I think the questions and the engagement and the feedback has been extremely positive. So it's been an excellent inaugural DIAS Day lecture. On my own behalf and on behalf of the Institute, would like to thank you. I'd also like to thank the School of Theoretical Physics at DIAS for organising the lecture this evening. We will have further lectures and events coming up, and in fact, perhaps some you've mentioned yourself some aspects of this topic around supersymmetry, etc., that haven't been looked at. So there'll be plenty of opportunity for exploration of some of these other areas into the future. And you've mentioned yourself, there've been a number of people at DIAS, whether Singer or Raftra, who've worked on a number of these areas. So just for the audience that are particularly interested in this topic, we would hope over the next year to be actually having some further lectures and talks. And in particular, J.L. Singh, it's the 60th anniversary of his publication on general relativity. We will be having a special event later in the year. For those of you who actually are on our mailing list, clearly we will be able to contact you about that. But if you're not, just email us, we'll put you on the list, or keep an eye on our website. I'm not sure, Denjo, whether Arthur would like to say a few words just by way of close, but for my own part, I would like to thank everyone for attending and all those involved in actually organising the event. And I think it's a marvellous way to mark our 80th anniversary.
Well, I'd just say thank you again. It was a great lecture. Good to see you. Good to see everybody. And nice to hear the story.
Thank you.
Okay. So thank you, everyone. And have a nice evening and a nice weekend.
And thank you again. Hope we can have you visiting here before too long in person. Thank you, Gerard.
Okay, thank you,
Absolutely.
Denjo.